This is example 8.3 in Discovering Design with Chemistry. A chemist burns 15 grams of zinc in excess oxygen. In other words, we have zinc plus oxygen happening and there's plenty of oxygen, so we're going to use up all the zinc. The result is 18.7 grams of a white powder. What is the empirical formula of the product? Because we have the conservation of mass happening, we know that if we used 15.0 grams of zinc and we added some oxygen with that, and we got 18.7 grams, the difference between those numbers is how much oxygen we used in grams. So let's start there. So we have 18.7 grams minus 15.0 grams. And that gives us 3.7 grams. We're subtracting, so the significant digits is just that we end in the tenths place there and there, so this one must also end in the tenths place. So that is how much oxygen we used in the reaction. So we know that these chemical formulas work with, when we're adding things up, they're going to be working in moles, they're not going to be working in grams. So we need some conversion relationships to this. So for zinc, let's pick a different color for zinc. So for zinc, which is right here, we have that 1 mole of zinc is 65.38 grams. And then for oxygen, we have 1 mole is 16.00 grams. So we can use those to figure out how many moles we used of each of these substances. All right, so for the zinc, we used 15.0 grams, and we know that for every mole, it's 65.38 grams. So when we divide that, and we need to keep 3 significant digits, we get 0.229 moles of zinc. All right, and then for oxygen, we had 3.7 grams. And when we convert that, for every 1 mole, we have 16.00 grams, and the grams cancel. Now, the oxygen probably burned in the equation as our formula was probably something like zinc plus O2 with some number here and some number here. But whenever we are using our conversion relationships to convert grams to moles and moles to grams, we always go back to how many that we have base, and so we're not going to worry about that O2 is usually part of a as an element that it's homonuclear diatomic. We just care about how much oxygen we used altogether, and so we're just thinking of it as an as part of a compound right now, and we're not thinking of it as its own little element because we're actually just focusing on the end results of how much. We don't care about what happened on the reactant side. We just know that we use this many grams, and so on the product side we still have this many grams, and on the product side the zinc and the oxygen are going to be together as that white powder. It's going to be some kind of zinc oxide thing going on. Anyway, so let's finish this up. With this one, 3.7 only has 2 significant figures, so our answer is also only going to have 2, so 0.23 moles of oxygen. Okay, so now we know how many moles that we used of both. We know that the compound that was produced contained 0.229 moles of zinc and 0.23 moles of oxygen, because that's how many grams we started with both, and we have to have that many grams at the end of both because nothing else was mentioned as being produced, and so we have the same number of grams, they're just combined in a way. And so to get the empirical formula, we have to remember that the empirical formula is really just a ratio of how much one element has to another element. It's not the exact number of atoms of each, it's just the ratios of the atoms to each. And so we can let's take the one that is bigger and put it on the bottom. So that would be the 0.23, and we're going to put the 0.229 on the top. So this is moles of zinc, and this is moles of oxygen. And we're going to see what that relationship is, or what that ratio of zinc atoms to oxygen atoms is. And whatever answer we get, we have to keep it to just 2 significant digits. Okay, so with this one, if this were any other number, we would keep these 2 and use the 5 to round it. Well, the 5 is going to round this up to a 10, or a 0 rather. It'll be a 10, but it'll round up the next one. And so when we round that up to just 2 significant digits, it becomes 1.0. So that's our ratio. That means for every oxygen atom, you can think of this as we turned it into a ratio. When we divide it, it's like we divided it and put that over 1. So for every 1 oxygen atom, we have 1.0 zinc atom. And obviously we know an atom is a whole amount. So we have the same number of each. We have 1 of zinc for 1 of oxygen. And so our empirical formula is just ZnO. Now that's not our molecular formula. It could be, but it's not for sure. But that is our empirical formula, meaning that's the ratio of zinc atoms to oxygen atoms in that white powder.